Okay, I think it's about time to start. The last session on applications. My name is James. I'm with Los Alamos National Lab. Thank you all for staying around for this last session. I know the sun's nice and flights are leaving soon, so thanks for sticking to the end. The first speaker is Harris Volos from University of Wisconsin. He's a graduate student, and he'll be talking about storage systems for storage class memory.
Thank you for the introduction. So I just came for us+, so I apologize if I cover some stuff that you have already discussed. I couldn't follow the discussions. So there we presented some work on exposing storage class memory as persistent memory. And this is really the next step of how to get persistent memory to the next step. So this talk is about some ongoing work in collaboration with my advisor, Mike Swift. And it's about built-in storage systems for storage class memory in user mode. The two characteristics of storage class memory that we are interested in is that they are non-volatile and can be accessed through ordinary load and store instructions, which really means that they have a memory-like interface that you can access them through. So as user mode can safely and directly access SCM, the operating system may no longer be necessary to mediate every access. So in fact, we argue that the current OS structure of file systems as kernel mode service is problematic, and we see two reasons for that. First, it limits flexibility, as it prevents applications from using storage class memory the way they see best, and it also reduces performance of SCM by introducing software layers that add significant latency along the access path. So our proposal is to move most of the file system functionality outside of the operating system up to user mode, and only keep in the operating system the functionality related to access control and protection. So this is an outline of my talk. I will continue by first arguing about the new opportunity that storage class memory enables, and then talk about our work in progress to build a user mode storage architecture that exploits this opportunity. So current operating systems structure their storage stack around a kernel-level file system. So the application invokes the kernel to store and retrieve data, and the kernel invokes a file system which invokes a block driver. So let's try to understand why we have this structure today of file systems as kernel-level service, and why this structure may no longer be necessary with storage class memory. So first, at the lowest level, block devices implement no protection, so they rely on operating system to protect them via the file system. Block devices also use DMA for read and write, which must be also be protected by the operating system, as DMA operates on physical addresses. Third, disks have long variable service latencies due to rotational and seek delays, so they can benefit from scheduling. And finally, disks are slower than RAM, so they can benefit from shared caching. So in addition to storing and retrieving data, the file system provides some other services, like sharing and protection between processes and users, and also providing a common naming system to easily locate data. So let's now see how many of these components are really necessary with SCM. So SCM can be protected by the existing memory translation hardware, so the operating system does not need to mediate every access to SCM. There's also no need for DMA, as SCM can be accessed directly by the CPU. And there are no seek and rotational delays, so there is no need for scheduling as well. SCM is nearly as fast as RAM, so there is no need for caching. And we see that many of the reasons for having a file system in the kernel cease to exist, so there is an opportunity here to streamline the storage stack. So in fact, BPFS, a research file system by MSR, Microsoft Research, recognized this. They attach storage class memory directly to the CPU and use a specially designed file system that exploits the characteristics of SCM. However, this proposal still keeps the file system in the kernel. So recent proposals by us and UC San Diego researchers go to the other direction and exterminate the file system by exposing storage class memory directly to user mode in the form of persistent memory. So while persistent memory makes it very easy and fast to persist any data structure in memory, they still rely on, persistent memory still relies on the underlying file system to have protection, sharing, and naming. So in summary, we see that recent work has acknowledged some of the opportunity with SCM, but they unfortunately limit flexibility by issuing SCM under a rigid interface, thus restricting usage to a single abstraction, namely either as a memory or as a file. So instead, we'd like to enable applications to use storage class memory the way they see best, while retaining the benefits of memory to have flexible data structures and the benefits of file systems to have sharing, protection, and naming. So we propose to move most of the file system outside of the operating system up to user mode and expose storage class memory via a thin veneer that its sole purpose is to allocate storage to its clients and enforce protection. And this will enable flexibility and performance. So a user mode storage system enables flexibility across 3 dimensions. First, implementation, second interface, and third abstraction. So implementation flexibility is desirable due to the existence of different workloads. So a storage system implementation should have the freedom to choose how to index data to better service its workload. So with today's disk-centric operating system storage architecture, any implementation flexibility comes at the cost of doing in-kernel development, which is a tedious and complex task. And people, to avoid this, often prefer to use a specialized file system, which they use solely as a storage pool from where they allocate chunks of space to build specialized storage systems in user mode. So, for example, the Google file system uses the file system as a storage pool, or the Facebook's Haystack photo storage uses the file system as a storage pool. The problem is that user mode storage systems are still coupled with the underlying file system, so any data access request has to go through the file system. In contrast, a user mode storage architecture that exploits the direct user mode access to SCM enables implementation flexibility without being coupled to an underlying file system. So while applications could also benefit from a specialized interface to files, today's applications are forced to use the generic POSIX file interface whenever they access files. So for example, a web server that simply reads a file has to perform 3 system calls, one to open the file, a second to read the file, and a third to close the file. So a specialized interface that allows opening, reading, and closing the file in one single system call could help improve performance. However, with today's storage architecture, you pretty much have to implement such an interface inside the kernel. However, with a user mode storage architecture, you can implement this specialized interface in user mode and avoid all these complex implementations in kernel. And finally, flexibility along the abstraction dimension is also important, as the file abstraction currently exposed by the operating system may not be useful for all applications. So for example, a relational database could benefit by a low-level abstraction that exposes storage as a collection of blocks than as a file. So overall, we believe this flexibility in designing the storage system is a unique opportunity enabled by storage class memory. Unlike disks, where any innovation across the storage stack has to be done pretty much in the kernel, which is hard and brittle, storage class memory enables implementing new interfaces, abstractions in user mode. So I'll now talk about the design of the user mode storage architecture we are currently building. This is work in progress, so I welcome any feedback you may have. So the goal behind this user mode storage architecture is to read and write file data with the least possible kernel intervention to get the best performance possible out of the SCM device. So we want to support services such as sharing, protection, name, and concurrency to be able to implement a user mode storage system which can be as generic as a file system. So we set 2 design principles to meet our goals. We provide naming and mapping between data and locations in memory in user mode. And we call into the kernel only when changing protection and allocating storage, for example, when we want to share data. So our current focus is on the structure of a user mode file system. So in the kernel, the SCM manager handles requests for allocating and changing protection of storage and keeps track of the storage allocated to each user mode file system. And in user mode, the file system is implemented as part of a library, which is linked against the application. And the file system is composed of 2 main components, the mapping and naming layer. So the mapping layer maps file offsets to SCM regions, and the naming layer maps names to files and can be the common to all of us hierarchical namespace. So to read a file, we first consult the naming and mapping indexes to locate the data in the SCM device, and then read the data directly from the device. So the key point here is that we can open and read the file without any kernel intervention. So to write to a file that has available free space or overwriting existing data can be done similarly to a read without any kernel intervention. You consult the indexes, which are in user mode, and then write directly to the SCM device. But here is a little more complicated case when writing extends the file. So it ends up involving the kernel. So after we consult the user mode indexes to locate where to write the data, we find that not enough space exists. So we ask the kernel to allocate some space on the SCM device. And then we create a new mapping to index the newly allocated SCM region, and finally write data directly to the SCM device. There are several challenges we need to address to have a full-fledged file system. Challenges include protecting the integrity of metadata, such as directories and inodes, and also to enable concurrent write access to files. So while we could address these challenges in the kernel, the reason we started this work is to really implement these challenges outside of, to enable these things outside of the kernel. So we believe we can do this, and by drawing inspiration from distributed file systems like Frangipani, we make the observation that in most cases you don't share. So you can pretty much work locally till you need to share, and at the point you want to share stuff, then you can invoke the kernel to make your local changes globally visible. So to enable this idea, we are currently exploring the use of leases. So a lease is a contract that gives its holder the right to work locally without worrying about others seeing its intermediate local changes. And you can release the lease to make your changes globally visible, or only release the lease when somebody else wants to acquire access to that storage region. So for example, here we have 2 instances of the same user mode file system that need to write to the same shared to the same file bar. So the first one gets the lease. It contacts the kernel to get the lease on that SCM region. And when it gets the lease, it can work locally, do the changes, and then release the lease to make the changes globally visible. So this work, as I said, is preliminary, and we are still exploring design options. So any feedback is welcome. So in conclusion, we believe that today's operating systems storage architecture does not fully exploit storage class memory. And our goal is to streamline the storage stack by moving most of the file system functionality outside of the operating system kernel up to user mode, and keep protection and access control only in the operating system. So this concludes my talk, and I'll be happy to take any questions. Yeah, so we're currently exploring how you could actually do that. But so when you allocate space, you contact the kernel. And the idea is that the kernel can enforce, if we are dealing with pages of storage class memory, then the kernel can enforce either read access only or read-write access. And then it can make sure that the one that asks both for the storage and the list, that only gets the read-write access to that storage region. And that's actually your list. And then if someone else contacts the kernel and wants to write to the same storage region, then the kernel can send a signal up to the user mode file system that you have to release the list. And so you have to pretty much complete what you are doing, make your changes visible, and release the list so that I can give the storage region to the other guy that wants to write. But the kernel is hoping that you do that. So if the user mode process does not abide, then does not follow the protocol, then you can either kill the process or
another question? No? No question?
How do you plan to protect against like malware? You know, since it's in user mode, he can directly access anything he wants, right?
Well, he can access only storage regions that has access to. So when I allocate some storage from the operating system knows that I allocate the storage. So anyone else that wants to get access, they have to go through the kernel, and the kernel can enforce that.
But you could change the local copy of the file system code and access anything you want, right?
You mean the user mode file system? But the code that you change, though, has to contact the kernel in order to get access to the specific storage, to the specific region in SCM that you want to get access to.
But there's nothing to stop it going to a different region because it's not going through the kernel.
No, in order to get access, it has to go to the kernel. After it gets access, it can do anything it wants by using normal load and stores to write to the regions. But in order to get access to it, it has to go through the kernel. That's why we say that we retain the protection and access control inside the operating system. But we believe that by doing that, we can effectively decouple the two things, like protection and implement the other stuff in user mode that can provide us more flexibility.
Yeah, what I meant is like you get access to region A, and then you just go ahead and access region B anyway, because you bypass the kernel.
But region, I don't know, should we take this offline? But okay. We're running out of time. Thank you.
I would just use fuse, but that's me. So our next speaker is Shivaram. He's a graduate student from University of Illinois. He will hopefully finally explain to me what consistent and durable data structures are in a manner I can understand. The title of his talk is Redesigning Data Structures for Non-Volatile Byte-Addressable Memory.
Thanks for the introduction. I'll try to do my best, James. So, good afternoon. I'm Shivaram, and I'm here to talk about redesigning data structures for non-volatile byte-addressable memory. This is work I did with my advisor, Professor Roy Campbell, and Niraj and Partha when I was interning at HP Labs. So I'm going to skip through the first few slides reasonably fast because at this venue, we've seen a lot about how DRAM scaling is facing significant challenges, and there are a bunch of devices which are being promoted as candidates to replace DRAM. These include phase change memory, memristor, and as we saw over the last couple of days, there are more candidates in the pipeline. So what are some of the properties that these devices are aiming to provide us? This is a more general view of what I think non-volatile byte-addressable memory will look like, and it's not directly specified towards one specific device. But all of these devices are aiming to provide non-volatile storage, which is reasonably fast at DRAM-like speeds of 50 to 150 nanosecond access times, and using being more scalable in the sense that you can have high-density devices within the next few years, and also use much lower energy than we have with DRAM-based systems today. Right? This represents a very interesting shift in the storage hierarchy, and to show why this is an interesting data point from the viewpoint of designing software systems, let's just take a look at these access times. Right? We saw them in the morning again during the keynote, where if you consider the processor clock cycle to be 1 nanosecond, you can see that DRAM access time is around like 55 nanoseconds, while writes to flash and hard disk are about in the order of microseconds or milliseconds. What this has traditionally meant is that I/O devices have been accessed over a block interface, and this has meant that there's asynchronous processing of writes and reads which go on to persistent storage. The newer memory devices like phase change memory or memristor promise to have access times much closer to DRAM than that of flash or hard disk. And this means that for once we have persistent storage which is really fast and which is much more closer to how we treat DRAM today rather than how we treat NAND flash or hard disk devices today. So what does this mean in terms of designing storage systems? And we saw this a little in the last talk also about exposing storage class memory to applications. So traditionally, disk-based data stores have a storage hierarchy of something like this, where you have a couple of layers of cache, and you have a DRAM layer, and your data is ultimately stored in disk. So to update anything, you fetch data from your disk into DRAM, and you update it in your volatile region, and it's then flushed back to disk periodically or asynchronously or something like that. Examples of this would include traditional databases, file systems, and many such systems. But these sort of systems have a throughput which is dependent on the disk speeds that you get. And since disk speeds are limited to the order of milliseconds, the performance of storage systems you get using the older architecture doesn't scale really well. So we've seen this slow transition towards modernly designed systems where you have necessity for doing really high throughput operations where the entire data is stored in DRAM, and the operations or the updates which come in are then made persistent by having a commit log which is stored on a flash device or on a hard disk, or it's like backed by a MySQL database. Right? For example, the Memcached clusters which are in use at Facebook or the Ramcloud project propose to use an architecture like this. So with the advent of non-volatile byte-addressable memory, there's a question of how do you expose this to applications so that you get the best performance, the best efficiency, and the best space capacity usage out of it, right? What we propose is that non-volatile memory be directly exposed to the applications, and we believe that this would actually lead to better performance because the applications can control exactly when data is being stored in non-volatile memory and how it's being flushed. And this is an example of the single-level store, which was also pointed out in the keynote earlier today. And this is similar to some of the design choices which have been made in earlier times, but it's just that the device right now supports byte-addressable non-volatile storage. So what are some of the challenges and opportunities which are given by making this design choice of having a single-level non-volatile storage layer? So for example, let's consider data structures and how they would be stored on such a single-layer storage device. In this example, I have a binary tree in which there are 3 nodes, 5, 10, and 20, right? And suppose I want to perform an operation, an update on this binary tree where I insert the value 15. So to insert the value 15, the first thing I do is I allocate a new node, and I assign a value 15 there. And I create a pointer from the node 20 to the node which is having the value 15. So there are two operations which need to be committed to non-volatile storage for the update to be successfully complete. However, suppose due to reordering of writes either at the memory controller level or at the cache line flushing level, you could have a situation where the pointer is written out first before the node containing the value 15 is written out. And if there's a power failure at this point or your process crashes, what would happen is you'd be left with an inconsistent data structure. And so the two important challenges we think are that consistency and durability needs to be maintained across failures when you're storing data structures directly on non-volatile storage. So far, I have motivated the problem that we're trying to solve. And next, I'll talk about consistent and durable data structures, which is one proposal to solve this problem. And I'll specifically explain how this works with respect to a Btree. Finally, I'll present some evaluation numbers from experiments which we've done. So the solution which we are proposing to this problem is a class of data structures called consistent and durable data structures. What we mean by that is these are data structures which have a similar interface to what you see from normal data structures, but they provide consistent and durable updates. So if there's a failure in between when an update is happening, you can still recover your data structure to a consistent form when recovering from failure. So how do we do this? We use versioning to maintain consistency across failures. And when you're recovering from a failure, you restore the data structure to its last consistent version. So what this gives us is almost like an atomic change across consistent versions of the data structure. We also propose to do this without adding any new processor primitives and using existing instructions from the x86 architecture to show how this can be done. To go a little bit more into detail of how versioning works, so the versioning that we are referring to is a totally ordered versioning scheme, and we use increasing natural numbers for this purpose right now. And every update to the data structure creates a new version of the data structure. So be it inserting a key into a tree or deleting a key from a tree, these operations are set to create newer versions of the data structure. And there's one special version number, which we call as the last consistent version. And this version number represents the version at which, the most recent version at which the data structure was consistent. So there are many uses for this last consistent version in that threads which are trying to read the data structure will use this last consistent version to get the most recent and up-to-date picture. And also when you're recovering, you will be restoring your data structure to the last consistent version. So having gone through some of the more generic framework that we've defined, I'll try to explain how this actually translates into a specific data structure by talking about a Btree. We picked a Btree because it's widely used in database systems and file systems, and it's also a complex data structure, so we can show what are some of the challenges that we face in such a design. The consistent and durable version of the Btree that we built looks similar to a normal Btree. You have a Btree node, which say is of size B, and each Btree node contains a key which determines the range of values that it's supporting. And along with the key, this is where it differs from a normal Btree. We store a start and end version number. As you can see, this is associated with each key inside the Btree node. And there's another notation which we use is that entries which have been deleted have their end version numbers filled up, and entries which are still live have a hyphen representing their end version numbers. And the entries which are deleted are marked in gray in the pictures that I'm going to use. So the start and end version numbers represent the version at which the key was created or deleted from the data structure, respectively. I'll walk over a couple of algorithms to give you a flavor of how the consistent and durable Btree works. For example, if you're doing a lookup in such a Btree, and we want to find the key 20 at version 5. So what we do is we first start from the root of the Btree, and we try to find the key which is greater than 20, which is the closest one greater than or equal to 20, and which is also live at version 5. Right? And once we find such an entry, we follow the pointer down to the next level, and we recursively repeat the search. This is very similar to a normal Btree lookup, except that you just make sure you're getting the key at the right version number, which is live with the right version number. The more interesting case happens in insert, especially when you have a Btree node which is full, and you're trying to insert another entry into this. So in a traditional Btree, what you do is you copy half of the entries to a newer node, but any failure which happens in between can mean that you could lose some data, and you could go into an inconsistent state. So in this example, I'll show what we do instead. We have a Btree node with the entries 5, 20, and 99, and we're trying to insert 40 into this node. Since this node is full, we need to perform an insert split operation. And in this case, what we do is we retain all the entries of the old node as they were, but we just set its end version numbers to 4. So what this means is we've marked all the entries which are there in the existing node as ended at version number 4, and we are going to copy all the entries which exist into 2 new nodes right now. So this resembles a copy on write or shadow paging-like approach whenever the Btree node is full. The important point to note here is that even if there's a failure right now, before we have finished the entire update, all the old data is still available in the existing leaf node. So 5, 20, and 99 are preserved as they were. So what this allows us to do is it allows us to, during recovery, to go and clean up entries which are part of the Btree at its most recent consistent version. So having built such a Btree, and there are more algorithms that I'm not going to go in detail here, the details are there in our paper, are that, so how would you use such a Btree in a data storage system, right? So we took a widely used open source key value store, and we said, can we integrate this Btree into that to show some of its benefits, and what are the pros and cons of using such a Btree? So we considered Redis, which is an open source key value store. And it's widely used in production by many of the companies today. And we considered this because it maintains its entire data set in memory. So Redis' entire data set is in memory, and it usually provides durability by having a write-ahead log of its own. So having considered this, we took up Redis and we integrated our Btree into it, and we built a data store which we call as Tembo, which is then the title of the slide. And we found that the experience of integrating the Btree into an existing data store was very simple, and we needed to change very few lines of code to actually do that. So there are more details about the Btree and about the durability techniques which we use to do this on current process, but there's details in the paper, and I'll also be happy to discuss that after the talk if you're interested. Moving on to the evaluation, we evaluated the consistent and durable Btree at 2 levels. At first, we looked at micro benchmarks to show how this compares to a normal Btree and also to a Berkeley DB implementation of a Btree. And we also did an end-to-end comparison where we took the key value store with the consistent durable Btree and compared it with its vanilla version. These tests were performed on a 15-node cluster with each node having about 48 GB of RAM. So there was about 720 GB of RAM in the entire experiment. So the first result that I'm going to go through today is the cost of versioning. So this experiment just measures how much overhead do we have just by maintaining these version numbers inside the nodes and performing these insert split operations. So what we did here was we compared a normal Btree, a vanilla Btree, with the consistent and durable Btree. As you can see there, we did millions of operations from 1 to 10, and we were inserting keys with 25 bytes and a value size of like 2K in this experiment. And we measured the throughput that we got in terms of operations per second for each one of these cases. As you can see, for the consistent and durable Btree, which has versioning overhead compared to the normal Btree, performs only about 10 to 20% worse for put and get operations, respectively. And we also found that the overhead sort of stays constant over doing 1 to 10 million operations, and we feel that this means that the overhead of versioning is negligible enough for us to for this case. Moving on, well, the next experiment that I'm going to talk about is how does versioning compare with RightHead logging? So what are the benefits of doing this mode of like durability? And in this case, what we did was we took Redis, which originally uses a RightHead log for maintaining its durability, and we considered two different cases. So Redis with using a Btree for its storage, and Redis using a hash table for its storage. And to compare it with our solution, we took Tembo, which is Redis integrated with the consistent and durable Btree. We again performed 2 million insert operations. Note that we only performed insert operations because that's where the impact of using a different data structure is there. And we used 2 client threads in this experiment and tried this for multiple value sizes from 256 bytes to about 4K. So the first result that you can see is that for a smaller value size, the Redis with the hash table and RightHead logging was performing better than the Btree cases. But as we sort of increased the value sizes, we found that the consistent and durable Btree outperformed Redis with the Btree and Redis with the hash table, with a win of around 30% over Redis with the Btree for 4K value sizes. What we think is happening here is that with RightHead logging, you have 2 changes to make. One is to update the log, and the other is to update the data structure in place. While for the consistent and durable Btree, the updates are only to the Btree itself. And since the insert split operations are amortized over a period of time, we don't have to do multiple writes for performing a single update. So this win we see is reflected as we increase the value size over a range of values. So I would like to call out that a related work, and our work is based on multi-version data structures, which have been used in database systems to do sort of time travel operations of going to database contents at different versions. And multi-version concurrency control has also been a technique which has used the observation that you can restore things to an older version during recovery. There are other in-memory data stores like EdgeStore or RamCloud, which can also use our ideas in order to use non-volatile memory directly on their system design. Finally, I'd like to point out that this is still a work in progress. We've only looked at data structures in this work of ours so far, and it is a challenge for it to be extended to transactions or SQL-like operations. In the morning's keynote, we again saw that supporting like partial rollbacks and other features like that might require more advanced techniques of maintaining consistency. And also, there are questions about non-volatile memory allocation and garbage collection, which will go on, which we have made assumptions of in this work, but are interesting challenges which need to be addressed. So in conclusion, what I'd like to say is that there are changes in storage media which are coming upon us in the next few years, and this is a good time for us to rethink the software system stack so that we get the best efficiency and performance out of next-generation storage systems. In this work, we've proposed consistent and durable data structures, which enable you to have data structures which are recoverable across failures. And using a single-level store, and by providing durability through versioning, we've explored some of the benefits of such a design. With that, I'd like to conclude, and I'll take any questions. Mm-hmm.
I guess I didn't quite understand, what that meant. I guess I didn't quite understand what you meant by that, what the implications are as you start building larger and larger data structures.
It's sort of independent of the size of the data structure. You can consider this to be something similar to knowing where your log record starts, or what was the last log sequence number you saw in traditional database recovery systems, right? So similar to that, it's some memory location or in your PCM or in any non-volatile storage where you can know that you have to start your recovery process from, and that stores a pointer or that stores the address for the version number that you have last seen, something of that sort. So that's a good question. I would say that since the version management scheme is relatively lightweight, you only have like a single version number to store. It shouldn't be a problem as long as you have a reasonable number of data structures. But it's something which is worth thinking about as to how you would have multiple of these and manage access to these easily. Yeah.
One more question? Thank the speaker again.
Thank you.
All right, the next speaker is Roger Pearce, PhD student from Texas A&M, who has spent some time at Lawrence Livermore, I believe. Not too bad of a drive up the coast. Huh? Roger's going to be telling us about some graph problems with the talk titled "Traversing Massive Graphs with NAND Flash."
Okay, thank you for the introduction. My name is Roger Pearce, and I'm a PhD student at Texas A&M. I am also a Lawrence Fellow at Lawrence Livermore National Laboratory, and this is joint work with my thesis advisor, Nancy Amato, and Maya Gokhale at Lawrence Livermore. So just briefly, I'm going to talk today for the next 20 minutes about some related work around our external memory graph algorithms and an asynchronous technique that we've applied to it, and an experimental study we've done using NAND flash that we submitted to supercomputing recently. So our overall objective in this work is to facilitate processing of massive real-world graphs. And by massive, we're talking about graphs on the order of billions of vertices and edges, maybe trillions. And these arise in domains like social networks, web graphs, intelligence community, and biological networks. And because of the massive size, it's very likely that these will not fit into main memory of someone's workstation or even a moderate cluster. And because of this is our main motivating factor for trying this out on merging persistent memory technologies such as NAND flash. So what we have developed, and I'll talk about, is a parallel asynchronous technique that we'll call async, that outperforms parallel competitors when we apply it to regular DRAM scenarios, so it's efficient. And using NAND flash as a semi-external memory, our approach is within a factor of 2 to 3 of DRAM performance when we use a Fusion I/O device for our external memory. Okay. So when I say traversing large graphs, the traversals that we have been experimenting with and I'll talk about today are breadth-first search, single source, shortest path, connect components. We've done a couple of other ones since this work, but these are the ones I'll talk about today. And our main view is that traditional graph traversal strategies are not well suited for these new storage devices. So we've proposed an asynchronous visitor queue algorithmic technique. It's a highly parallel approach for graph traversal, and the key benefits of this approach is that we exploit fine-grained path parallelism in the graph data. We can tolerate data latencies to and from the external memory device. We can transparently support shared memory and external memory, and hopefully a generic enough technique for many graph algorithms. The asynchronous visitor queues are conceptually similar to a traditional visitor technique if you're familiar with this for graph processing. A visitor is a generic vertex or edge level abstraction, and it's essentially a small function that's applied to individual vertices and edges in a graph. The key difference between our approach and a traditional sequential visitor queue approach is that in a sequential visitor, often a visitation framework enforces an ordering, so you could have a breadth-first search visitor or a depth-first search visitor. Because ours is asynchronous, such an ordering isn't enforced, and it must be programmed into the constraints of the search. So next we'll move to some what I mean by semi-external versus external. So in the graph nomenclature, an external memory graph is defined as a graph that any portion, the vertex or the edge set, cannot fit in main memory. For a semi-external case, we say that we can store O of V data information about the vertices in the graph in main memory. However, we can't store the edges in main memory. And more specific to our work here, what we end up getting is a read-only graph data set stored completely in the persistent memory, and output of our algorithm and temporary algorithmic data is stored in memory. Graph algorithms have been well studied for external memory devices. Much of the work has been done with a theoretical model called the parallel disk model, and the main underlying assumption of this model is that the cost of I/O is significantly larger than the cost of computation. For undirected graphs, known algorithms exist for sublinear I/O in terms of the graph vertices and edges. However, for directed graphs, for general directed graphs which we're interested in, no known sublinear I/O algorithm exists. And what this means is for a traditional rotating disk, a billion vertex graph could take 47 days or something like that to do a traversal on. With the advent of NAND flash and other technologies, this underlying assumption is challenged because I/O is now orders of magnitude faster than disk, and parallel computation and concurrent I/O is very important now. Throughout the rest of this work, we'll talk about some parallel libraries that we've compared to. We've done experiments with the multi-threaded graph library out of Sandia. It's primarily designed for the Cray XMT supercomputer. However, they do have implementations that run on x86 systems. The SNAP library uses OpenMP for threading, and we also have done experiments with the parallel boost graph library, which is a distributed memory machine. And the main algorithmic consideration that we've taken in this approach when we use NAND flash is that highly concurrent I/O is mandatory. This plot shows on the x-axis the number of threads for a random I/O benchmark. These types of traversals are highly random access, versus the kiloops per second for reading. And we have 3 devices that we've been experimenting with, the Fusion I/O and 2 SSD devices made by Intel and Corsair. And the takeaway from this is that even on an 8-core AMD system, we need at least 32 threads or more to fully utilize these devices. So our algorithm and our applications have to be able to do that. So next I'll move to the actual graph asynchronous technique. Again, our design goal is to provide a parallel technique that's efficient in memory and traverse graphs in semi-external memory at comparable performance to in-memory. And the key ideas are the high data latency through an asynchronous I/O and computation, exploit fine-grained path parallelism, transparently support shared and external memory, and a generic technique. Again, we use a visitor pattern, and the visitor queues that we use are priority queues, and the priority is algorithmic dependent. So if you're computing a shortest path or a breadth-first search, the queues are prioritized by minimum path length. If you're doing a connect component, your queues will be prioritized by the component ID. And each thread in our multi-threaded system, again, we said we needed lots of threads. Each thread owns one of these queues and is in charge of some subset of vertices in the graph. And this means that vertex-level locking is not required. We have locking at the queue level, but not locking on an individual vertex. And just briefly, we'll talk about one example of an algorithm in this. We'll talk about single source shortest path. And this is a fairly simple example, and I have an illustration next. The algorithm starts off by all the vertices have some path length parameter that's initialized to a large value. And we have visitor queues, and each visitor queue is prioritized by the minimum path length. And we start a visitor at the source vertex of the traversal with a path length of 0. Inside of the visitor, when each vertex is visited, we visit a vertex with a tentative bound on the path length. If this path length is less than the current known path length for that vertex, we update its information and we queue outgoing visitors asynchronously for the outgoing edges. So to illustrate this, we have a very simple weighted directed graph here. The vertex identifiers are shown inside the bubbles with the edge weights. When they first initialize all of the path links, the second value here, to a large number, and then we queue a visitor to the start vertex. So over here we have a pictorial example of our visitor queues, and in this example we have 5 separate threads, 5 separate visitor queues. Each of these is prioritized by the minimum path length. So we start at the source. The thread that owns this queue picks up the source visitor, visits it, executes it, updates its path length, and queues outgoing visitors to the outgoing edges. And there's no synchronizations in between here, so I have to go through this quickly. The traversal proceeds and continues to queue visitors into the visitor queues for neighboring vertices. And oftentimes things can arise such that visitor queue, because it's asynchronous, path length of a larger value shows up before a smaller value, and this just has to be taken care of asynchronously and recomputed. And this asynchronous traversal proceeds all the way until there are no visitors remaining in any of the queues, and we globally, the algorithm converges when everything is empty. And we've done connect components, breadth first search, shortest path, and a number of other algorithms and very similar techniques, each with small variations on how the visitors work. So now I'll talk about the experimental study that we have done and submitted to Supercomputing 2010. We have 2 types of machines that we've done our experiments on for these experiments. The first, we have a machine that has 16 AMD Opteron cores and 256 gigabytes of memory. This machine serves as what is our baseline if we had enough DRAM to do all of our experiments. And then we have semi-external experiments are done on a 16 gigabyte memory DRAM machine that has 3 different configurations of NAND flash devices: Fusion IO with PCIe, Intel with SATA, and a Corsair with SATA. It's important to note that between these 2 machines, the exact same motherboard and CPU cores are used. The only difference between these 2 machines is the amount of memory. We've implemented our asynchronous approach using compressed sparse row data structure. It's a common data structure for implementing directed graphs. We use POSIX threads. For external memory approach, we have 2 versions. We have one that uses a standard I/O using the pread command. We also have an mmap version. And we directly mmap the data from the Fusion I/O or the persistent memory device into main memory. To fully utilize the random I/O performance of these devices, we're oversubscribing the threads up to 256 threads on 16 cores. And I mentioned that we have the visitor queues are implemented as priority queues. Additional to the algorithmic priority, which is algorithm-based, we have a secondary key priority, which is the vertex identifier, which increases aggregate page level locality in a compressed sparse row format. So again, we've compared to a number of parallel graph libraries that I previously mentioned. We also have done we normalize our experiments to baseline sequential versions, namely the Boost Graph library and the Dymax reference SSSP solver. Data sets that we have been interested in using are scale-free, so-called scale-free or power law distribution graphs. We have a synthetic graph generator that we use called RMAT. It has now been adopted by the Graph 500 benchmark. It's been recently released. With this synthetic graph generator, we generate graphs up to 1 billion vertices and 16 billion edges. We also have a number of web graphs that we've done experiments on. The largest is up to 8 billion edges. So just to summarize the questions that we want to ask in our experimental study, the first question we want to ask is how efficient is our asynchronous technique when we have enough DRAM? So completely in memory, is an asynchronous technique going to be efficient? The second question is how efficient is this asynchronous technique going to be when we use persistent memory to store a device, to store our data? We answer these two questions by showing experiments using a machine up to 256 gigabytes of DRAM, comparing to open source graph libraries that I mentioned. And for the semi-external experiments, we have the 16 gigabyte machine with flash memory to store the graph data sets. So when we have 256 gigabytes of DRAM, we're just comparing the asynchronous, parallel asynchronous algorithms performance using the data sets that we've experimented with. Our asynchronous approach outperforms the competitors using 256 gigs of DRAM. This held true for both breadth first search and single source shortest path. On the x-axis of these of the graph here, I'm showing the graph data sets. This is the vertex size, so this is the largest graph data set at 1 billion vertices, 16 billion edges. And the red bars is our asynchronous approach. The green bar is MTGL, and the blue is SNAP. And we're showing the speed up over a sequential algorithm. So our approach is able to not only is our approach able to outperform the competitors, but we get parallel speed up to 12 or 13x on 16 cores. Now, when we move to semi-external memory, which is the main focus of our work, we have done our experiments such that we're showing the speed up over the sequential algorithm on 256 gigs of DRAM. So anything over the unity line here means that our approach is able to outperform a sequential algorithm in DRAM. The blue bar is our approach, our asynchronous approach, using 256 gigabytes of DRAM. So this is an upper limit of our semi-external algorithm. And then the red and the green bars show what our external memory approach using Fusion I/O, either with the standard I/O or IMMAP interface. And the takeaway message is that using 16 gigs of DRAM with Fusion I/O, we're within a factor of 2 to 3 of DRAM, of parallel DRAM performance. And this is with 1 billion vertices and a 16 billion edge data set for both breadth first search and connected components. To put in perspective how much external memory we're requiring for this, the directed graph data set is 72 gigabytes, and the undirected data set for connected components is 136 gigabytes. So we, in our work at supercomputing, we showed a number of other experiments with both synthetic and web graphs. For our semi-external memory experiments, we showed what I just briefly showed using Fusion I/O, we were able to get within 2 to 3x of a fully parallel DRAM performance. Using the other devices, Intel and Corsair, we were able to get, for almost all cases, above the sequential algorithm's performance in DRAM. Just to summarize, we proposed a parallel asynchronous approach for graph traversal. We've demonstrated the performance in breadth first search and connected components. Our approach outperforms parallel competitors when using shared memory or DRAM. And when we use NAND flash as a semi-external memory, our approach is within a factor of 2 to 3x of the DRAM performance when we use Fusion I/O. So that is it. Are there any questions? The short answer is I'm not quite sure. We had to do a lot of monkeying around to get IMMAP to work well, and that I assume is going to be very similar to a swap behavior. So I think that there's a lot of Linux issues that would have to be addressed to get in a perfect world. But the important factor from the algorithm's point of view is the asynchronous approach being able to be highly multi-threaded, oversubscribed threads, and also able to prioritize the queues by not only the algorithmic information, but also by locality, essentially, so that we can increase locality in these data sets that are otherwise very random. So it's conceivable you could do it in a swapped device also, the same approach. It would just probably need to have some Linux hacking.
Why was the mmap process in the POSIX IO?
Well, the POSIX IO interface for every visit to a graph edge or graph vertex requires calling a system call pread, right? And we are able to extract some level of locality. So even on, so say a page hit, which is data sitting there in the page cache, we have to call that system call. With mmap, it's already there. The page tables are set up in virtual memory. However, up to like maybe 2 months ago, mmap was terrible, and there's still, if anybody has experience with multi-threaded mmap, getting it to work well in this scenario, definitely love to hear about it.
Speaker again. All right, we have one more speaker. So you people that are leaving, please turn around and sit back in your seats. The next speaker is Dr. Harumi Kuno. She's a senior research scientist at HP Labs, and she'll be speaking about database software from non-volatile byte-addressable memory. So let's go blue.
How do I get this thing to display? Oh. The people up there, okay. Well, while I'm waiting, I'll get the mic adjusted. Can you all hear me back there? Can you still hear me? Uh-oh. Okay, how's this? Ah, there we go. Okay. So it's just as well they didn't have me presenting right after Shivanov because our titles are so similar. Okay. So the first author on this work, while we're waiting for this to come up, is Graefe, and I'm Harumi, and I'm going to talk about some techniques that we can use to incorporate byte-addressable NVRAM into database systems, into a database management system. How do I make, where's the mouse? Sorry. This? No.
I don't know about that.
Oh, okay. Sorry. There we go. Okay, so here's a picture of what a database system looks like on the inside. And I'm sure that if we put our minds to it, we could use NVRAM to improve every single tiny little bit of it. But that's not the subject of this talk. What I'm actually going to talk about is if we wanted to use NVRAM as the persistent storage, then what's the minimum that we have to touch? What's the components that we absolutely must modify? And the answer for that is the transactional storage manager. The transactional storage manager includes components like the access methods, which organize data on disk, the buffer manager, which lets us stage I/O to the disk for the database, the log manager for recovery, and the lock manager to support concurrency. And now let's talk about what does the transactional storage manager do? So in general, transactional software is responsible for, as you might expect, taking data that users write and update and storing it on the persistent storage and then reading it back. And the persistent storage can be NVRAM. And in addition, it also is responsible for some functionality that's behind the scenes that the users don't see, which is recovery, verification, and repair. So what we're going to talk about here are some techniques for implementing these things for NVRAM and what do we have to change and what changes when we have NVRAM versus disk. And being realistic, our design goals are that we don't want to destroy the balance, that delicate balance between functionality, efficiency and performance, and software complexity. So for example, if we add some new functionality, but it makes testing really difficult or completely disrupts some existing architecture, then that's bad. But we believe that if we make some really careful choices, that we can leverage NVRAM and make the overall system more principled, less complex, and maybe more efficient too. That would be good. So that's the goal. So now I'm going to walk through 4 techniques. So the first decision was that even though NVRAM is byte-addressable and is not itself natively page-oriented, we want to keep the abstraction of pages. And the reason for that is, first of all, because it lets us contain insertions and updates, changes to the databases, faults and repairs, so that when you change something on the database content, you will impact only a small part of the overall data structures. In addition, staying with this page paradigm lets us remain compatible with existing mechanisms. For example, we can support incremental backup to page-based storage, such as disk, because as Mohan pointed out this morning, probably disk is not going to go completely away, right? Note that we do have to reoptimize page sizes. In fact, that's one of my questions for you, but we can take that offline. Because when you're dealing with memory, NVRAM, instead of disk, then your cost models are going to change for optimizing disk sizes. Okay. Second decision was, let's rethink the buffer pool, which Mohan touched upon briefly earlier. So a traditional disk-based system uses the buffer for 2 things. First, to compensate for the difference between the slow access time for disk and the fast access time for memory. And then second, to implement write-ahead logging, which enables concurrency control and recovery. And the way traditional, so the black letters there are showing what exactly write-ahead logging means. So the way write-ahead logging works is first you get your data off of the disk, you put it into memory in a buffer, you modify the data in the buffer pages, and then the buffer hangs on to those dirty pages until the change has been logged to persistent storage. So in other words, it's do, log, and then you write the data to persistent storage, and then you can use the logged actions for redo and undo and redo. So the thing is that NVRAM doesn't have the slow access times of disk. So do we really need to copy everything into the buffer pool? But if we don't, then what are we going to do about write-ahead logging? And that's what Mohan said was going to be tricky. Okay. So the technique we have to offer here is a new solution called log shipping to self. We call it that. And basically, we take that original do, redo, undo, and we get rid of the do, first of all. And then second, we try to avoid using the buffer pool. So the way this works is when you want to change something in the data, instead of taking the data off of the NVRAM and sticking it into the buffer pool, you create a log record first. Before you don't do, you just create the log record. And then you persist that log record to persistent storage. And then instead of doing a do, you do a redo. You apply your redo. And this means that, like write-ahead logging, the log record is being saved before any database update takes place. So, in other words, we've taken do, undo, redo, and we changed it into undo, redo log. And this means that we can avoid using the buffer pool. It supports existing write-ahead logging, and it's simple. And furthermore, what we've done here is we've broken the tie between the user action and the log action, and now the updates, the actual update of modifying the data on disk is now tied, and is now being driven by the log records as opposed to the user threads. So this means that we could work out a system to defer the database updates until sometime after the log has been persisted. Of course, this will require us to maintain some other data structures to support the queries so that they search the log records. But it does open up some new possibilities. The third decision is online verification of Btree storage structures. And I'm not going to go into the details here at all, but the big picture is that a database system may become corrupt, and that traditional offline consistency checks First of all, they're offline, so they work upon a snapshot, and by the time the consistency check has completed, it's likely that that snapshot has become completely out of date. Okay? Or existing methods for online concurrency checks are not complete. For example, they don't check referential integrity. So we believe it's necessary to have an online technique that will do a complete check, just root to leaf, all the way down. Okay. That's not so exciting, but we need to have it because the next stage is we want to have single-page repair. So in a traditional system, there's three things you can repair. You can recover from a transaction failure using the undo, the redo, rollback. You can recover from a system failure, for example, cleaning up after the system has crashed. Or you can recover from a media failure, like the whole disk has died, and now you have to, or the whole disk array has died, and now you have to recover. But NVRAM, as we've seen, can fail locally. Now, at this point, I was reminded of on the first day, somebody said, you know, the disk drive is doing this too. Well, we'll see. We'll see what happens. Maybe this will work well. So we believe that we need a fourth recovery form, which is for databases, which would be page-level recovery of one or more individual database pages. And again, I'm not going to get into details, but the trick is over here that within the log, when we made those logs before we did our updates, we linked the pages associated with, we link the records associated with each log page together so that we can very efficiently search the log, find all the log records associated with a given page, and apply them in an efficient manner. And that's the trick. So, in summary, we've proposed some techniques to help NVRAM improve both the complexity and performance of a database system. And it comes down to those four tricks. How am I doing for time? Okay, very good. And the conclusions are that we believe that software that supports transactional retrievals and updates does require updates, but it does not mean that we have to make everything more complex. And we believe that that by trying to keep things really simple, by trying not to upset existing balances, and trying to think about what are the characteristics of NVRAM that we want to exploit, that we could come up with some good solutions. That's it. I think I breezed through that. Yeah. Any questions? Sure.
I have a problem understanding your decision number 2. You were saying instead of do, you want to do a log and then undo redo. So suppose decision number 2.
Okay, log shipping to self. Okay, so okay. So the way a disk-based system would work is you would get the data off of the disk and you'd read it into the buffer pool, and then you would make the changes to the data in memory, and then and while you're doing that, you would create a log record, and then you would write that log record to persistent storage, and then after the log record is written, then you would update the persistent storage. So if you forget about the part about the data being updated in memory, the important part is what happens on the disk or on the persistent storage. And what happened there was that first the log record was written, and then the data was changed on disk on the persistent storage. So this is doing the same thing, except it's skipping the part where you go and you get the data and you put it into memory and you change it in memory. Instead, it's going straight to write the log record and then update the data on disk. Well, you might still have a buffer pool, but you're not going to use it for this. You don't need to use it for this. Oh, and I forgot, actually. I completely forgot to say, one of the advantages of doing it this way is that now you've made redo very important to your performance. And that means it's going to be very well tested. and it's going to be optimized. It's not going to be this emergency thing. It's going to be the thing that is the default operation. So we believe that will make for a more robust system anyway. So instead of implementing do and also implementing redo, we just implement redo and we do it really well. That's the idea. You still look skeptical. Do you think it's not going to write, or?
No, I'm just saying. I'm just thinking if every write without a buffer pool, basically every modification to the data you write to the non-volatile memory. Wouldn't non-volatile memory get wear out very fast?
You're writing to a log, so. Yes, but you have to modify the data. Okay, so the other thing is you don't have to modify every data in place right away here, because you're actually, this is, do you remember or do you know about the log structured file system or log driven systems? So this is a little bit like that, because the important thing is you have your log records that you're appending. So you have this append log, and you have these log records, but you don't have to go and update your data on storage right away, because you can do your queries through the log.
But that's different. The log structured stuff, they still have a buffer pool. So if you modify data 100 times, you modify it in the buffer pool 100 times, and then you don't modify the data on this specific time. But in your case, you don't have a buffer pool. So every modification, in-memory modification, you basically modify the non-volatile memory.
Well, you don't necessarily have to modify the memory, but you do have to write a log record. So you're right in the sense that if you were to do, say, 100 or 1,000 really, really rapid updates of one value, then you would get 1,000 log records here this way, unless we were to come up with some clever scheme to get around that. But nothing says that you have to go and invoke the redo action for every one of those log records. You could just wait until the end and execute the redo once. No, you don't have to.
So maybe you should take this offline, and we'll see if there's any other questions. I don't mean to cut the conversation. But
Okay, sorry.
Are there any other questions? No? All right, let's thank our speaker again, please. That's it for the presentations. I think maybe Steve has a few words of wisdom for us.
I don't have a lot of wisdom left. So that is it. Thank you so much for coming. I think this has been an enormous success. We'll be sending a questionnaire in a couple of days to get some feedback from you about the workshop and anything you think we could do better, or things you liked in particular. I would like to take a chance to thank a bunch of my students who helped out with the website and the submission site and doing the travel grants and getting the USB keys together, and also Iris Villanueva and Betty Manulian from CMRR, who made all kinds of things happen without Paul or I even knowing about it, which was awesome, like the food last night, for instance. So let's give them a round of applause. And otherwise, we hope to see you again next year. This seems to be going pretty well, and we're going to try to do it again. There's a question.
I just wanted to make a comment to everyone here, since we got in December from Fusion.io. I just wanted to let everyone know that this week we launched what we're calling our Academic Advancement Program. And so for people doing research in government or academic groups, if you guys buy a card, we're willing to donate a second one to your research project. So if people are looking for equipment on NSF dollars, we're going to try and help you guys out.
2-for-1 special. All right. Thank you all so much for coming.